So we continue today our study of electromagnetic fields and quantum mechanics and particles in those electromagnetic fields. So last time we described what we must do in order to couple a particle to an electromagnetic field. And the rule was at least simple. You get the Schrödinger equation, and the Hamiltonian is now changed into this form. If you had a free particle, you're accustomed to have p squared over 2m. That has changed, and you have a new term with p minus q over c a squared. Thank you. So now our task is to understand how this is compatible and what are the implications of these changes. They're pretty significant changes. This expression, p minus q over ca, is what used to be just p, and that used to be just the kinetic energy, and now looks a little more strange, in fact. So in terms of electromagnetic potentials, we know that the potentials are not unique. There are these gauge transformations that establish that these are completely equivalent potentials. So two potentials, A and phi, and A prime and phi prime, are physically equivalent. They define the same electromagnetic field if they are related in this way. We then mentioned that, therefore, you have an issue with the Schrödinger equation. You would want the physics to remain invariant under gauge transformations. So you could write the Schrödinger equation for the new gauge potentials with A prime and phi prime, and you could compare with the Schrödinger equation with the old potentials, A and phi. And you could ask, okay, is it solved by the same wave function? And the answer is no. The wave function must change, but there is a way to get one wave function from the other. Here is the formula. Psi prime and psi are related by this factor, this function u, which involves exponential of the gauge parameter multiplied by a couple of physical constants, including the charge q of the particle. Now, we're going to use the notation q all the time. Many books put E in there, and that's the charge of the electron. And then you always wonder, is that E or minus E, or which sign is it? So here, q is the charge of the particle. If you have an electron, q is minus E. But let's leave it q open there so that you can work with arbitrary charges in any circumstance. So this Hamiltonian is what we have to understand. I want to make a couple more comments about what this Hamiltonian is, and we must think a little about the gauge invariance as well. So there it is. Hamiltonian contains this term squared. So let's just ask ourselves, what does that term really imply? Well, there's 1 over 2m. So for the Hamiltonian, 1 over 2m, and we have this factor squared. So following the careful things we're accustomed to do in quantum mechanics, I would put p squared here minus q over c p dot a minus q over c a dot p plus q squared over c squared a squared plus q phi. That's how the Hamiltonian looks. But you have to be careful. here, this term, we kind of understand what it is. It's vector potential squared, no problem. Here is p squared. We're accustomed to that. That's a Laplacian. We have two terms that could be a little strange. A dot p probably is all clear. A is dotted with a vector momentum, which is an operator, is the gradient. So that's going to differentiate whatever is to the right. The question is, what is P dot A? And P dot A must be thought in the operator way, that P acts on everything to the right, including A. So if this Hamiltonian is to act on a wave function, that doesn't mean that the P operator just acts on A. It acts on A and everything to the right. So P dot A, if you think of it as a derivative, is h bar over I divergence of A plus A dot P. You see, this P is h bar over I gradient, but it's acting on everything. So you could put a psi to the right of here, and it would act on everything there. So you should, maybe in order to justify this equation, you should just write h bar over I gradient acting on A times a wave function psi, and go through this and see that at the end of the day, this P dot with A means act on A, but then you still have to act on everything to the right. So that's this term here. So this term is pretty important. Sometimes your A satisfies what is called the Coulomb gauge, in which del dot A is 0, but in general it doesn't. So this helps clarify what the Hamiltonian really is. It would be a mistake to say that these two terms are the same, and it would be also a mistake to say that this thing is just the divergence of A. Both are wrong things. So this is the whole Hamiltonian now is P squared over 2m. Then you have twice, well, let's have this term. So you have plus, the I goes to the numerator as I h bar q over 2mc divergence of A. And that's just the divergence of A, the function. It's not anymore a differential operator. It's just acted on it. Then you have this term twice, so minus q over mc A dot p plus this term q squared over 2m c squared A squared plus q phi. So that's the Hamiltonian. Let me just make sure I got it right. P squared over 2m plus iqh, yep, minus q ap, yep, q squared. Well, that's right. Okay, so this is our Hamiltonian if you just want to write it very explicitly. It's not generally all that useful to have the explicit form, but in some examples, there will be at least one example where it is nice to know. And it, in fact, the H formula on the top of the blackboard hides in a nice way a little bit the complexity of this whole coupling. Yes? Yes, this is for a scalar particle. So we're taking a particle without, at this moment, without spin. For spin particles, there would be a little extra term sometimes. Let's say a couple more words about this thing, in particular the gauge invariance. So we now have seen what the Hamiltonian is. Let's think of the gauge invariance. How could you establish this gauge invariance? So an identity that is very useful takes the following form. H bar, this differential operator, H bar over I, gradient, the P, minus Q over C, A prime times U, and you could put a psi here if you wished, is in fact equal to U H bar over I gradient minus Q over C A psi. Okay. So I call this a very remarkable identity. And look what's happening here. This is useful for this kind of equation. If you have a psi prime, which is u psi, the factor u interacts very nicely with this operator. In fact, as you move u from the right to the left, the gauge potential goes from A prime to A. A rather nice thing about this derivative is as if this derivative had a very special symmetry property that u can be moved across as if, almost as if u was a constant, but of course it's not. But when you move it across, the only effect is to change the A prime to A, so a gauge transformation on the A. That is the reason this derivative equipped with an extra term is sometimes called a gauge covariant derivative. That is, it transforms nicely under gauge transformations. It does a nice job. I write this equation because in part of the exercises you will have to do, you will be asked to show that this statement about gauge transformations is correct. That if this equation top holds, the bottom equation holds with the replacements indicated here. And this identity makes the task of proving the equation, the gauge invariance, very simple. Because you can imagine this psi prime put u psi, and then getting the u out, so the psi prime just will become psi, and the u going through these factors and simplifying very nicely. So this is a simple equation to show. For example, I can take the left-hand side and see what happens. So the first term, you have a gradient acting on the product of two functions, and that's just the gradient acting on each. So h over I, gradient of u, times psi, plus u, h over I, gradient of psi. That's the first term. The second term is minus q over c, a times u psi, because a prime is a plus gradient of lambda. So then I have minus q over c, gradient of lambda, u psi. So I wrote the first line. Now we can take the gradient of u. U is here. When we take the gradient of u, what do we get? H bar over I. Now gradient of u. You differentiate the exponential, so you take the gradient of what is in the exponent. So it's I q over h bar c, gradient of lambda, times u itself, because you're differentiating an exponential, times psi. And then you have all these other terms. I'll couple this term. These two terms here are plus u h bar over I gradient of psi minus q over c. U and a commute because a is a function of x and t, and u is a function of lambda, which is also a function of x and t. So there's no momenta here. These two things commute. So u can be moved to the left. A psi minus this term. And if we've done the arithmetic right, the first and last term should cancel, and they do. The I cancels, the h bar cancels, there's q over c times that, and there's minus that term, so these two cancel. And this is precisely the right-hand side. So this covariant derivative is very nice. There's something about the Schrödinger equation, of course, that in a sense, it's all made of covariant derivatives. Let's look at that. So any version of the Schrödinger equation, here is the typical version of the Schrödinger equation. So recall that the vector potential in general can be thought as a 4-vector. You may or may not have seen this in electrodynamics, but it's just like time and x form a 4-vector, the scalar potential and the vector potential form a 4-vector. So the 4-vector with index mu 0, 1, 2, 3 form this. And then if you look at the Schrödinger equation, what do we have? We have IH bar d psi dt minus q phi. I'm bringing the last term on the right-hand side to the left. So it's minus q times phi, which is minus a0 psi is equal to 1 over 2m. This h bar over I gradient minus q over ca squared on psi. And now look at this. It can be written as follows. Minus c as times h over I, 1 over d over d of ct minus q over ca naught psi equal the same thing on the right-hand side. So I've rewritten the left-hand side in a slightly different way. All the terms, so I put an extra c down this d ct. That cancels the c, the h bar, the I went to the denominator. And now this all looks like this covariant derivative. Look at this covariant derivative, h over I ddx minus q over ca. And here it is, h over I ddx0, the zeroth component of the covariant, minus q over ca naught. So the whole Schrödinger equation, it's built with these funny derivatives, ddx minus the vector potential acting on it. These are the covariant derivatives. These are nice operators. You see, the operator P is always called the canonical momentum. Canonical momentum. And this canonical momentum is a momentum such that x with p, if you put a hat, is I h bar. But this canonical momentum p is not mass times velocity. Not at all. This canonical momentum is a little unintuitive. It's the one that generates translation. The one that is mass times velocity is really this whole combination is mass times velocity. Because if it's mass times velocity, this term, 1 over 2m times mass squared times velocity squared, that gives you kinetic energy. So we have to beware that the canonical momentum is not necessarily the simplest, most intuitive object.